All right. Learn Smart will be due tomorrow night, and homework for Chapter 8 is due on Wednesday. So I've extended them one more day for you. Because I want to try to finish up Chapter 8 today, talking about nucleophilic substitution. Remember we were talking about last time on Friday, the role of solvents in these reactions. And there are a lot of different kinds of solvents and have a range of polarity from completely nonpolar like alkanes to polar molecules which have some functionality in it that allows a dipole for the molecule. And for substitution reactions, the presence or absence of an acidic hydrogen in the solvent also can influence the reaction because we're affecting the different properties of all the various things that are happening, all the various components in a nucleophilic substitution reaction. So depending on what's most important for the rate determining step, the solvents interact with those different components in different ways and can affect the rate, if those are involved in the rate determining step. So in an SN2 substitution, we find that the absence of those protons in the solvent are best because in the rate determining step, it's a one-step reaction. The nucleophile is reacting with your alkyl halide at the same time that the halide is coming off. So you need to have a strong nucleophile. So you don't want to inhibit the reactivity of the nucleophile at all. But you still need to solubilize or dissolve the polar reagents. So for example, sodium hydroxide, we need polar solvents in order to get them into solution and dissolve them. Because they are ions. And we want polar solvents because the transition states in any substitution reaction involve breaking the bond to the leaving group, so that inherently provides for a polarization of that bond. So in the transition state, you have a greater polarization of bonds as well. So you have developing charge. The leaving group comes off as an anion usually when we're talking about an anionic nucleophile. And you need to stabilize that by polar solvents as well. But if you have protic solvents, the nucleophile here is very important in this one-step reaction. So if you have protic solvents that are hydrogen bonding, that stabilizes it too much. Okay, so then the reactivity of the nucleophile is decreased, and that will affect the rate of the reaction. Okay, since it's involved in that step, the only step. Make sense? Yes? Okay, and a substitution reaction which occurs by first formation of a carbocation, it's not necessary that we have a strong nucleophile because in the rate determining step, once you form a carbocation, the rest is going to happen. That's the slow part, the hard part. So the ability or the how you interact with the nucleophile is much less important. What's more important is that you're stabilizing the charged species, the carbocation and the halide ion as it comes off. And here we still need polar solvents, but protic solvents help to do that a lot.
So polar solvents just help to stabilize.
Polar solvents will help to stabilize it. Since we don't care about having a nucleophile interacted with these protic solvents, it doesn't matter. This actually, a polar solvent, regardless of whether it's protic or not, will stabilize ions. But hydrogen bonding provides more stabilization. So it's not that an SN1 reaction can't occur in a polar aprotic solvent, but it works best when you have the protic solvent. That's all. You certainly could do SN1 and form carbocations in solvents that don't have protons on them, but it's best. Okay. So if we really take a look at all the features that we've been talking about for the differences between these two reaction mechanisms, it's summarized in this chart here. So the substrate, the nature of your alkyl halide or the leaving group, the organic molecule, is going to be one of the important things to dictate whether the reaction goes by a direct substitution SN2 or by a formation of a carbocation. And that depends on the ability to form a stable carbocation. So if it's a tertiary substrate, it can form stable carbocations, but it's not going to be able to do direct SN2 attack of a nucleophile because it's too crowded. Okay, so that's complementary. Tertiary substrates for SN1. Primary works best, so the less crowded it is for SN2, and secondary can work as well. You need a strong nucleophile if it's involved in the rate determining step. If it's not, a weak nucleophile or even a neutral nucleophile like the solvent or water or methanol or something like that works just fine. In both cases, we want to, the reaction is always better if you have a better leaving group. That is a weaker bond and then a more stable anion that comes off. That makes for a better leaving group. The stereochemistry of the reaction depends on whether you form a carbocation or not. So if you form a carbocation, then you lose the stereochemistry that was at that leaving group to begin with because you've now formed a planar p orbital. Whereas in an SN2 substitution, the direction of the formation of the nucleophile carbon bond has to be 180 degrees from the leaving group, so everything inverts. Okay? And now the solvent. Polar solvents are required. Protic ones work best for SN1, but we can't have those protons there. It'll inhibit the SN2. Okay? So all these things we've been covering in the last few lectures, and it's sometimes a little difficult to keep this all in mind and put this all together. That's why I'd like to summarize things in these kinds of comparative charts. It gets more complicated because these reactions form similar intermediates and can affect the structure in a different way, and that is we have this problem. Okay? We have competing reactions oftentimes in substitution reactions where we can, instead of doing substitution, we can do elimination. So whether we have conditions which favor carbocations or conditions where we have a strong nucleophile or a strong base, these can compete. So if you think about the example where we have an SN1 substitution reaction, what would happen in an SN1 substitution is that your nucleophile would react with the carbocation to form your substitution product, right? But if that is a strong base, what can happen instead, or if it's basic at all, what can happen instead is the E1 elimination path. So these are competing pathways, right? Competing pathways. So we can instead form a double bond instead of the substitution. And sometimes we see mixtures. E2 elimination is the same thing. If you have a good leaving group and your nucleophile does SN2 substitution by backside attack to form the new OH bond, then that SN2 substitution would give the nucleophilic substitution product. But that can compete. If there's a proton anti-periplanar with the leaving group on an adjacent carbon, all those pathways we talked about before with elimination can also occur. Okay, so how do you think we would be able to control of all these possibilities, whether you go with the formation of carbocations or not? There are multiple pathways available to those kinds of reagents. Okay, so how would you influence it or direct it one way or another? Any idea? Yes?
Or that the basicity of the this.
The basicity, absolutely. Elimination works best when you have bases or ions. If you're going to do formation of carbocations, if you have anything negatively charged around, even if it's a low concentration or weak, most likely it's going to be protonate. The other thing is, in the case of substitution SN2 versus E2, the crowdedness of that carbon is going to be important, right? So if you start to put substitution in those positions and make this more crowded, that's going to block this. But this hydrogen here is still readily accessible. You don't have to get as close to do elimination as you do substitution. So that plus the strength of the base versus strength of the nucleophile, and those are two different properties really, can help us out. So if we look at some examples, some comparisons of substitution versus elimination. The two most important factors, the basicity of your anion and the structure of the alkyl halide. Okay, this is an example where we have a pretty strongly basic reagent, sodium ethoxide. Okay, sodium ethoxide in ethanol. If we do this reaction, not under ideal SN2 conditions. So notice we have a protic solvent. So that's decreasing the ability of that to be nucleophilic. But it's still kind of a strong base. What we see when we take 2-bromopropane, you see two products form. One is the substitution from SN2 reaction, and one is the elimination product from E2. Those are competing. But the major product here, you can see 87% is the elimination product. Okay, strong base, not the most ideal solvent, but a pretty good solvent, not the most ideal solvent for SN2, and a secondary bromide. Okay, secondary is in that middle area. It's getting pretty crowded, so it's much easier for that base to take a hydrogen off of a carbon adjacent to that. It doesn't have to come nearly as close to that crowded carbon, and it does E2 elimination quite readily. Whereas if you go to a primary bromide, you see that selectivity for which path it goes changes. Now, a primary carbon is readily accessible for SN2, okay? And so what we get is about a 90%, 90-10 ratio of the substitution versus elimination. So here it's just a difference. We haven't changed anything. This is just showing the difference in both in pretty strongly basic or nucleophilic conditions that the substitution, the crowding around that halide is dictating which pathway is preferred. Okay? Questions about that?
It'll depend on the strength of the base and whether or not you're going to get
The strength of the base, right? And I'm using, by the way, in general, oxygen anions are pretty strongly basic. So they tend to give more elimination than, say, other nucleophiles. Like if you go down the periodic table to sulfur-based nucleophiles, they are much less basic, but more still very nucleophilic. So then you get better competition for the substitution over elimination. So the basicity of the anion and the structure of your substrate are important. Let's see, what do we have here? So this is showing you a little bit, this is a figure from your book, showing you how that crowdedness affects things. So if you have your alkoxide trying to form a bond to that carbon, it gets pretty crowded in that 2-bromopropane. But taking off that hydrogen to do elimination is much easier. Okay? So if this other group wasn't here, if that was just a hydrogen, it'd be much easier to get in and form that bond. Okay, sometimes that crowdedness isn't necessarily on the alkyl halide itself, but if you have a very bulky base, an anion, like if you take the salt, sodium salt of tertiary butyl alcohol, it's still an alkoxide, but now the base itself is very crowded. It's bulky. So it's very difficult to do SN2 substitution with a bulky base. Instead, it would much rather deprotonate to form the double bond. So this is now a primary bromide. Let's say we just had one bromopropane. What we see is very little of the direct substitution product, and a major product is the elimination product. So that's a trick we could use also. If our substrate isn't bulky enough to prevent substitution, and we want to do elimination, we just choose a base that is very big and hard to do the substitution reaction with. Okay, so you can play around with those depending on your choice of base. Here's an example, base strength versus the nucleophilicity. One example of a good nucleophile is sodium cyanide. It's not a very good base. Cyanide is not a very good base, but it's a terrific nucleophile. Okay, and so even if we have a secondary substrate, a chlorine, which is a little less reactive than a bromine as a leaving group, still the only product we get in this reaction is the substitution product, because we've changed now the nature of the base. And notice we're in ideal conditions for SN2 substitution. Dimethyl sulfoxide is an aprotic solvent. And so everything is right for doing very selectively the SN2 substitution reaction. And in this particular example, we don't see any elimination. Okay? We don't see any elimination. So that's an example of where a good nucleophile is important. So remember, that's you. Is that a birth or a death?
I don't know.
One example of a good nucleophile. Some other good nucleophiles might be things like, as I mentioned, the thiolates. So if we were to compare, let me wipe this. If we were to take sodium hydroxide versus sodium sulfide, okay, the top case would most likely favor elimination, particularly if we had this in water, okay, as a solvent, or some other protic solvent. And sodium sulfide, SH minus, is essentially non-basic. I'll just say weak base. Whereas this is a strong base. So if we keep in mind that basicity is not necessarily the same as nucleophilicity, you can get by with this also. This will lead to substitution. If we use the sulfur nucleophile, sodium hydroxide would probably give a lot of elimination in this case. Okay? Here's an example now of some SN1 versus E1 type of processes, or it could be E2. You don't need to form a carbocation. A tertiary substrate like this, 2-bromo-2-methylbutane, this can undergo substitution or elimination, depending on the conditions, but it can't do SN2, right? SN2 not possible for this because it is just way too crowded. Notice these conditions. If I just take this in methanol with nothing else present, just dissolve it in methanol and heat it up, what I get is a major product being the substitution product and a little bit of the double bonds. There's two possible isomers of the double bond as well, right? Depending on where you take the proton off of. So the major product in that case is the substitution by an SN1 pathway. Okay. These must be formed from an E1 pathway to give those two products. Now if we have in here, instead of just ethanol, we have sodium methoxide, we would probably see very minor amount or probably none of the substitution, depending on how much sodium methoxide we have present. If it's very, very low concentration, you might form some carbocations, but generally if you have any kind of basic conditions, carbocations aren't that likely. But elimination pathway can occur regardless of whether you form a carbocation or not. So we could have, here's a couple of hydrogens, right? As long as you have a base present, you could do elimination, E2, from that proton or that proton. Sorry, the arrows are terrible. And that would give these two products as the major product now in the case of having a base present. Okay, which of those would be the major double bond? Two possible isomers, constitutional isomers, right? The more substituted double bond is favored. Zaitsev's rule, remember? Don't forget the stuff we learned before. It's very important. So in this case then, with a tertiary substrate, I think it's somewhat easier to control elimination versus substitution, particularly if you want elimination. It's always easiest to control elimination by having strong bases present. That is, if that's what you want. Okay? Your book talks a little bit about this leaving group for substitution chemistry. And so I want to go back. I talked about this a couple of lectures ago. And that is the sulfonate as a leaving group. It is very useful, and they're very good leaving groups. So to bring you up to speed, a sulfonic acid has this structure where you have some kind of carbon group attached to, so that's a carbon, alkyl or aryl, attached to an SO3H group. It's an acid because it has that proton. A specific example, one that's used a lot, is this one, which is para-toluene. By the way, that P, we'll learn about it in another chapter later. Para stands for the position of substitution on this ring. Para-toluene sulfonic acid. So this is a toluene group. You can have many kinds of sulfonic acids. If it's a CH3, SO3H, it's methane sulfonic acid. We can have trifluoromethane sulfonic acid. Those give different properties to that sulfonic acid group. And the chlorides of those. So if you replace this OH now with a chlorine, this is a para-toluene sulfonyl chloride. And these are quite reactive electrophiles. This sulfur has a lot of positive charge. That chlorine can be displaced. For example, if you just take water and take para-toluene sulfonyl chloride and react it with water, you'll substitute the chlorine for the OH. Okay, so notice that reaction, instead of water, we do the reaction with an alcohol. So we have an alcohol here. Just like water, it can react at that sulfur and exchange for that chlorine. The byproduct here is HCl. A proton comes from the alcohol, and Cl minus comes from the para-toluene sulfonyl chloride group. And what we've done now is form a bond from what was the original alcohol. Now we've formed a bond to that sulfur. Okay? Pyridine, and if you're interested, pyridine or some other, usually some kind of tertiary amine we add in here because that has a site which can be protonated by HCl. It neutralizes the HCl. Another one that's used commonly is triethylamine. Triethylamine is also used as a base sometimes in these reactions. Often I will abbreviate that ET3N, triethylamine. Okay, so what have we done now by putting this group on the oxygen? What we have done is take this carbon-oxygen bond. OH minus is a terrible leaving group. Okay? You can't do direct nucleophilic substitution on an alcohol. How did we do substitution before with alcohols? In chapter, what was that, chapter 5, 4? Alcohols and alkyl halides. How did we do substitution of alcohols? You had to protonate it. We had to do it under strong acid conditions because OH itself is a terrible leaving group. Only if you protonated it and made it an oxonium could you then split off water. That's not always, you can't do SN2 chemistry in strongly acid conditions, right? Because you need strong nucleophiles. This, however, let me clean this up a little bit here. By making this tosylate, a tosylate group, by converting the alcohol to a tosylate, what we've done now is made that CO bond much more reactive. We polarized it. We've made it more like an alkyl halide in terms of its reactivity. Okay, this is now a partially positive carbon and a partially negative oxygen. And that's because this is an electron withdrawing group. Okay, electron withdrawing group. It's a really good leaving group. By the way, I sometimes abbreviate this as a TOS. Your book, I think, uses just TS. Or here would be OTS, tosylate. They're essentially the same. Well, why would that be a good leaving group? Why would that make that carbon-oxygen bond weaker and make that come off easier? Well, if you think about the anion, let's say we do a nucleophilic substitution and we kick this off now with the electrons and break that bond, right? What is the anion leaving group? That's a sulfonate anion, right? So if you imagine now this negative charge is not just located on that one oxygen. You can draw resonance forms where you can put the negative charge up on the oxygen on top, or you could also delocalize the negative charge to the oxygen on the bottom. And so actually the negative charge is spread out over 3 atoms, all 3 oxygens. That's stable, right? What makes good leaving groups? The weaker the bond, the more polarized the bond, and the more stable the anion if it were to break. Those all go hand in hand too. The more electron withdrawing that group is, given a specific bond length, the more stable that anion will be. The more easy it will be to depart. Okay, so how strong is it? How good of a leaving group is it? Here is a chart from your book showing various leaving groups and the relative rates of a substitution reaction. And what you can see if you look at the halides, we've been talking mostly about the halogens. So fluoride, terrible, the worst leaving group. Okay, it's essentially inert. Relative to water as the leaving group, water meaning it's protonated and comes off. Okay. Iodide is even better leaving group than neutral water. So iodide is better. Bromide is about as good as an HO3 plus or that you have on there. But the sulfonates, if you just go with the methyl sulfonate, it's 10 to the 4th times a better leaving group than bromide or water. Okay? The tosylate, the paratoluene sulfonyl, is an order of magnitude even better leaving group. And if we start to put more electron withdrawing groups, the more we stabilize that anion, the better a leaving group it is. 10 to the 8th times more reactive than bromide. So you can see these groups are very useful to be able to take an alcohol, which is essentially unreactive for SN2. Now we can make it into a sulfonate without changing the nature of the carbon-oxygen bond at all, make it a really good leaving group, better than a halide. Okay, and that's useful. That also has important stereochemical consequences. Okay, so if we think about the substitution reaction, where we react with a nucleophile and do an inversion of configuration in an SN2 reaction, sometimes we definitely want to be able to control that, right? And we want to be able to selectively, at will, get one product or the other, one stereoisomer or the other. And this is how you can do it. If you start with an alcohol, where you have the exact same stereochemistry, this is the, which configuration? RRS. Yeah, that has the S configuration, so does the one on the bottom. And we want to make a cyanide. We have the ability to make either an enantiomer of the cyanide, depending on how we carry out this reaction. Because if we make a tosylate, we have original stereochemistry S configuration of the alcohol. If you make a tosylate, all we've changed is we've replaced the OH bond for the O tosylate bond. We have not affected or changed the CO bond at all. Okay, so that doesn't change the stereochemistry at all. This is still S. Okay? Then we can do a nucleophilic substitution with something like a cyanide as a nucleophile. This is an SN2 reaction, which goes with inversion of the stereochemistry. So we end up with, and actually that group has the same priority relative, so this is the R configuration. So we start with the S alcohol. We can do one inversion, make the OH into a good leaving group without changing the stereochemistry, and then do an SN2 reaction and invert it. Okay? Or if we want to get the same S stereochemistry, what we need to do is simply do two inversions. Right? We do two SN2 reactions in a row. So OH, we can convert it into a good leaving group with inversion. Right? Remember, if we take SOCl2 or PBr3, that activates but then kicks it off with a halide to make an alkyl halide, and it does that. That is an SN2 reaction, though we haven't really talked about all those details now. So that goes with inversion of configuration. And then you react with a cyanide, it inverts back to the original stereochemistry. So it's doing two inversions in a row. Inversion, inversion. These are both involving an SN2 reaction at some point. One to get the bromide on, one to exchange that for cyanide. Okay, so we have the tools now to be able to control from the same starting material which stereoisomer of the product and get only that stereoisomer. Isn't that cool? I think it's cool. You guys need to think it's cool. I want you to think it's cool. It's really cool. We have power as organic chemists. Molecular architects, right? This is really a full-fledged summary of all of this. Some of these are gray areas, and some of these are areas where we have complete control over how things will go, or pretty good control. So if you look at this, what I've done is summarize all four of those possible competing mechanisms. We have SN2 versus E2 on the right, and SN1 versus E1 on the left. And I've organized this by the type of substrate, because it actually turns out, of all the factors involved, the nature of the substrate substitution is one of the critical ones. Okay, so if we have really unhindered systems, or primary substrates, the good news is you're never going to form carbocations. No carbocations. Okay, so SN1 and E1 mechanisms aren't going to be possible with a primary substrate. And so you're left with, well, we need to figure out how to control SN2 versus E2. Both of those could be favored. And in that case, then, it depends mostly on the type of reagent you're reacting with. Is it a good nucleophile or a very good base? Okay, if it's a strong base, notice if it's a strong base, we're always going to favor E2 eliminations across the board compared to strong nucleophiles. Okay, sometimes that goes hand in hand and it's some competition, sometimes it's a very clear difference. Like cyanide versus hydroxide. Which one would favor E2 and which one would favor SN2? Cyanide or hydroxide? Cyanide will favor what? SN2. Hydroxide would favor E2. Okay? We saw one case where with a primary and a very unhindered alcohol alkoxide, we can get a significant amount of SN2 and only a little E2. But generally, if there's any kind of bulk there, if it's a secondary substrate, okay, if it's a secondary substrate, the nature of the nucleophile is going to be critical. Okay, strong nucleophile, but not a very good base, definitely SN2. Strong base will probably favor E2. Okay. So then it is possible to form some carbocations in the middle, but never ever under basic conditions. Okay? Keep that in mind. Carbocations, you're not going to form under basic conditions. It's always going to be under neutral or acidic conditions. So you can avoid a secondary substrate doing any kind of carbocation formation just by having some kind of anion basic conditions, nucleophilic or strongly basic. Okay, so that you can control. Tertiary substrates, favored to form carbocations. It can't do SN2 substitution, so that X means it won't happen. Remember that E2 elimination only requires approaching a hydrogen adjacent to the leaving group carbon. So if you do have a strong base, or sometimes even weaker bases, if you have an anionic base, or you can do E2 elimination on a tertiary substrate. But if there are no anions present, carbocations can be formed, and then depending on the nature, you can get a little bit of E2, E1 elimination, but depending on the nature then of the bulk of your neutral nucleophile, it would favor substitution or elimination. Okay, does that help put this all together a little bit? There is nothing which is absolute, and that's the problem. When you have competing reactions of reactants, they do what they want to do. They'll always follow the lowest energy pathway, but it depends on how much difference two pathways' energies are in the transition state. If they're close in energy, you're going to get mixtures and less selectivity. If they're much further apart in energy, the lower pathway is going to win out to a larger degree. So that, again, is another way to look at the various factors involved. Now, what can influence this as well? What can influence the base strength, or the nucleophile strength? What don't I have up here? Substrate substitution, a little bit of solvent, favored in protic solvents. These, I didn't say here, favored in aprotic solvents for SN2. So your nucleophile strength can depend on the solvent you're doing it in. You can take the exact same substrate, exact same nucleophile, and if you have protic solvents or aprotic solvents, you could get a difference between SN2 and E2. Okay. But here are some examples of substitution reactions. What I have are two different conditions, conditions A or conditions B, for each of these substrates. And I want you to think about what pathway or what kind of product would be formed in those conditions. Okay, so in this case, we have this substrate. What's the nature of the substrate? It's a primary alkyl halide. So that rules out something right away, right? What does that rule out? No carbocations can be formed. Not possible. So SN1 or E1, not an option. Okay, here are two conditions which should be, these kinds of conditions should give you almost exclusively or largely major one pathway. And so the major pathway in conditions A, sodium cyanide and this aprotic solvent hexamethyl phosphorus triamide. What do you think is going to happen? What reaction mechanism? Come on. SN2, right? That's going to be an SN2 reaction, so the product will be substitution of the bromine with the cyanide. Okay? The product of A. Okay? Cyanide is not a very good base. It's a much better nucleophile. In the bottom case, we have B, which is a tertiary butanol, so we have a protic solvent. That's going to make a nucleophile weaker. And we have a strong base, which is very bulky. Okay, bulky base, tertiary butoxide. What's that going to favor? E2, so what's the product? Where's the proton that comes off? Here, right? So your product will be alkene. See how those conditions are different? Now, here's something I hadn't really talked too much about. It's in secondary bromide. And here I have, the difference here is, I didn't put the solvent on, I assume it's like ethanol or something. Here's just a difference in the nature of the reagent. Here I have sodium acetate, which looks like this. And here I have sodium ethoxide in B. Okay, so just thinking about the nature of those reagents. Which one should give you more substitution and which one would give you more elimination? Which one's a stronger base? We have acetate or ethoxide. Ethoxide will be the stronger base, right? The acetate has resonance structures. You can spread out that negative charge. So the acetate is a weaker, much weaker base. The ethoxide is a stronger base. So this one should favor E2 elimination. This one should favor the formation of the double bond. Whereas the top case, you'll probably see some elimination as well. But it's secondary, it's not tertiary. You can do substitution on that. This would probably undergo, give a significant amount of nucleophilic substitution, which would be that. Okay, SN2. Why? Well, it's a very, very weak base relative to this one, ethoxide. And also, it's since those electrons are held, by the way, the acetate, since it's held a little bit loosely, those electrons are spread out, but not held very tightly, they could be available to forming bonds. Remember we talked about nucleophilicity? It still can be a pretty decent nucleophile, even though it's a weak base. All right? And the last case, tertiary, only we're not going to be able to do SN2 is not an option, right? So it could only do E2, E1, or SN1, depending on whether you have a strong base or not. So if we just take this in ethanol and heat it up, what do you think the major product will be? SN1. Okay. So that would just give you a substitution where we put the ethanol. That's the only nucleophile present. Ethanol will replace the bromide. And in the top case, strong base, it'll favor E2. And E2 could occur in two ways, actually. We could form that bond or that bond. Okay, elimination would be major. Now, all of these will probably be some mixtures, but those are the major products that would happen under those conditions, most likely. So, yeah, hopefully that helps you get a sense as to some of these differences in conditions and how it can affect the course of the reaction. I want to show a couple other examples. I'll actually ask you, what happens if I take something like this? That's a bromine, even though I can't draw very well. And I take this molecule and treat it with a base. One base that's really good for deprotonating alcohols is sodium hydride, Na8. What do you think is going to happen? I changed things a little, right? I have an alcohol, which I'm deprotonating and making an alkoxide by that base. attached in the same molecule as a carbon with a leaving group. Guess what? It can work. It works just fine. Sodium hydride will deprotonate this. You'll make the sodium salt here. Okay, and that will react with that carbon in an SN2 reaction. It just happens to form a ring. It's a really good way to make ring compounds. The product is that. Okay, that's a very useful way to make ethers. This use of sodium hydride to deprotonate an alcohol and then react with an alkyl halide can be done between two molecules, alcohol and bromide, or within the same molecule. And it can be used to make something like this. Oh, come back then. How do you think I could make that? From this. Well, you learned in the alkene chapter, anyone remember there's a one-step way to do this? Using per acid, metachloro per benzoic acid. But you can also do it in another way. You can do this by treating this with bromine in water. Okay, what is that form? From the last test, you should know this, right? Bromine on one side, water adding on the other. Look, I have an OH group, and I have a carbon-bromine bond in the same molecule. I simply treat this with sodium hydride. That takes off this proton, makes a negative charge, and then it cyclizes and forms an epoxide. It's actually a good way to make epoxides. And those are easily obtained from alkenes. And so by taking all these different reactions we're learning and thinking about how we can combine them together, you can see how we have a lot of ability to make lots of different things. Okay? I think I'm going to stop there and I can talk about this. We can talk about this at another time. We will be beginning the next chapter on alkynes on Wednesday. So we'll see you then.